CIT 1123, Module 1, Subsection 3, OSPF operation. This is the final section of this particular chapter. We'll get into the configuration of OSPF in the next piece. And in this part, they just go through the operational states. This is all just objective information that you can write down and memorize for multiple choice exam questions that you are sure to get. And they are sure to ask you questions about what state are you in if the hello packets are received from a neighbor. And they contain the router ID of the sending router, and you're going to transition to the two-way state. And you say, well, I'm obviously in the initialization state. I'm in the init state. So you get the basic idea. You start in a down state, and then you go into the initialization state where you start sending and receiving hello messages. In the two-way state, the communication between the routers is bidirectional. Each router knows that they're talking to each other. And if necessary, they'll set up what's called a DR and a BDR, which means a designated router and a backup designated router. And that only happens on multi-access links. That means Ethernet for the most part. If there's a switch between routers, and there's a nice picture coming up here. And we'll talk about that a little bit, about how the router ID helps form the DR and the BDR, because there's a lot of packets that are going back and forth to form neighbor communications. And if you have a lot of routers that are actually on the same subnet, same network, they're all going to be neighbors to each other. But do they really need to tell each other about what's going on? And the answer is no. What they'll do is elect a designated router for that segment or that network, and then if there's 5 or 6 routers that are all connected to the same and they have an update to send, they'll send it to the designated router. The designated router will then send it to the other 4 routers that are on that system, and that will expedite and make an efficient use of communication rather than every router telling each other exactly what they're doing. Backup designated router is just there in case the regular designated router happens to be the one that falls out of service. So keep that in mind. The states move on into the X start state, where the networks decide which router will initiate the database descriptor package exchange. So remember, when routers first start up, they're going to want to talk to each other and tell each other everything they know. That's that database descriptor packet exchange, and they're going to talk to each other and tell each other everything that they have. Once that's set, it's in the exchange state. Once that information is then processed by the receiving router, you're in the loading state. And in a full state, you're at full convergence, and your router knows exactly where every network within the system is. So that's pretty good. Establishing the neighbor adjacencies. This just talks about the, really the cold hard facts of setting up a neighbor. The neighbors are found through multicast addresses, so every device that is running OSPF will be using multicast addresses 224005 and 224006 for sending and receiving those packets, and for sending their OSPF messages back and forth. So it is a multicast solution. It's not a broadcast solution, which takes down a little bit of the overhead of the devices communicating with each other, and that's pretty much how it goes. Nothing super exciting there. Neighbor relationships, you can read through this on your own. I'm not going to spend too much time on those slides. Synchronization of the databases, like I said. Here's the thing. Once these things are set up, you are in a pretty good state, meaning that your routers now know about all of the links. And after your updates are sent, and then it says, well, when are they going to send updates? Well, we're going to send an update every 30 minutes, so we'll do a little sanity check just to make sure everybody's where they're supposed to be. And then if there is a change in the system, hey, this particular network's no longer available, you'll send an update to your neighbors when that change is perceived, and that will trigger them to then reevaluate what's in their tables. Other than that, once every device knows about all the paths to all the destinations and has sorted out what the best paths are and started putting those in their routing table, there's not a whole lot to do. They can just kind of sit back and just pass traffic back and forth. This slide talks about the need for the designated router, and this is what I was talking about before. So in this case, we've got 5 routers that are all in the same subnet, right? So each one of these routers is going to want to send out hello packets to each other. So let's take the router in the top left-hand corner. It's going to send out hellos, and it's going to receive acknowledgments from 4 of its neighbors. It's going to, oh, this is great. I can get into a neighbor state, and I can send a database descriptor to each one of these. And then if there's a change and this is where things get weird. If there's a change to anything that's sent, I'm going to set a link state update to all 4 of my neighbors. And then here's where it goes wrong, is if there's a change within this guy's system, and he sends it to all 4 of his neighbors, each one of those neighbors is going to send an additional 3 updates to their other neighbors. So when this device receives that change sent from above, it's going to fire off that change back to this router and this router and this router. But it's totally unnecessary because they already received the change from the original router. So in order to stop this procedure from happening, and that's going to happen over and over again, right? So all 4 of these receive the change, and then each one of those 4 sends 3 updates to each one of its neighbors, letting them know that they received the change, and no one cares anymore because everybody received the change the first time. So what's going to happen is we're going to use a value called the router ID, and we'll talk about how to set up a router ID when we get in the configuration chapter, when we do chapter 2. And each router is going to then compete for the role of designated router. And there's a couple different ways to set it up, but the first way that they set it up was this. Highest IP address on any given router is the router ID. Of course, we can now set them as primary, and we can change a cost value that goes along with it. But let's just say this router is the designated router. So what will happen is that any changes that are made, all the routers know that they're on a shared system. They're in an Ethernet or a multi-access system. But if there's any changes, there's any link state updates that need to go someplace, they're all going to go to the designated router, and then the designated router will send one update to each one of the other ones. So let's review this again. So top left has a change, and let's say that the designated router is now actually middle bottom, right? So top left has a change. Top left sends the change not to all of the neighbors, but just to bottom center. Bottom center receives the change and then sends it to just the other 3 neighbors. Now everybody knows about the change, and the change is known, and there's no extra packets floating around utilizing your bandwidth for no good reason. So that's the reason for that designated router. Second highest IP address gets the backup designated router. You'll see this. This will become more. We'll do more on this in the next chapter, in the next module, I should say. And also, there is a really good lab on it. So there's a packet tracer lab where I talk you through the whole thing on there as well. Okay?